Tonight, we are going somewhere close, not to another galaxy, not to some abstract corner of the cosmos we can barely imagine, but to a world we can almost touch. A world that sits right next door, glowing pale red in our night sky, close enough that light from its surface reaches us in just 3 minutes. Mars. You have seen it 1,000 times, in movies, in headlines, in the dreams of billionaires and engineers who talk about colonies and terraforming and humanity's next great chapter. But tonight, we are not going to talk about the future of Mars. We are going to talk about its past. Because what scientists have found on Mars in the last 3 years has quietly rewritten everything we thought we knew about the red planet, and possibly about life itself. Here is what most people do not realize. Mars was not always the cold, dry, rusty desert we see today. 4 billion years ago, Mars had oceans, real oceans, deep, blue, stretching across the northern hemisphere, enough water to cover the entire planet in a layer over 300 meters deep. It had a thick atmosphere, it had clouds, it had rain, it had rivers that carved channels so wide you can still see them from orbit. Mars was, for hundreds of millions of years, a planet that looked remarkably like Earth. And then something happened. Something catastrophic. The oceans vanished. The atmosphere was stripped away. The surface was sterilized by radiation. Mars died. Or did it? Because in September 2025, NASA's Perseverance rover found something in an ancient riverbed that made scientists around the world stop what they were doing. Inside a rock from a dried-up river channel in Jezero Crater, the rover detected a pattern of minerals and organic carbon arranged in a way that, on Earth, is only produced by living organisms. Leopard-spot textures of iron and phosphate, threaded with veins of organic material, locked inside a mudstone that formed at the bottom of a lake billions of years ago. Then in Isidididi, 26, Curiosity, still roaming the surface after more than 14 years, discovered the longest chain organic molecules ever found on another planet. Molecules so complex they resemble the building blocks of life on Earth. And that is not all. We now have radar evidence suggesting there may be liquid water, right now, today, trapped beneath miles of ice at the Martian South Pole. Tonight we are going to walk through 7 shocking discoveries that have transformed our understanding of Mars. We will start at the very beginning, when Mars was born from the same cloud of dust and gas as Earth. We will watch it grow oceans, build an atmosphere, and develop conditions that could have supported life. We will witness the catastrophe that killed its magnetic field and allowed the solar wind to slowly peel away everything that made it habitable. We will follow the robots we have sent there, the orbiters, the landers, the rovers, and see what they found in the rust and rock and ancient sediment. We will confront the 60-year-old mystery of the Viking landers and their baffling experiment results that still divide scientists to this day. And we will end with the most important question humanity has ever asked: are we alone? By the end of tonight, you are going to understand Mars in a way that most people never will. Not as a dead world, not as a future colony, but as a crime scene. A planet that may have once been alive, that was murdered by the cosmos, and that might still be hiding survivors beneath its frozen surface. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand what Mars is today, we need to go back to the very beginning. Not just of Mars, but of the entire solar system. And the beginning was chaos. But first, let us take a moment to appreciate just how close Mars is and yet how alien. Mars orbits the Sun at an average distance of about 228 million kilometers. At its closest approach to Earth, called opposition, that distance shrinks to about 55 million kilometers. At its farthest, when the Sun sits between us, it swells to over 400 million kilometers. This dance of distance is why Mars changes brightness so dramatically in our sky. Sometimes a brilliant amber beacon rivaling Jupiter, sometimes a faint reddish dot barely distinguishable from the background stars. A year on Mars lasts 687 Earth days, nearly twice as long as ours. A day on Mars, called a sol, is just slightly longer than an Earth day, 24 hours, 39 minutes, and 35 seconds. This is an eerie coincidence. Of all the planets in our solar system, Mars is the only one with a day length even remotely similar to Earth's. The tilt of its axis is also similar, 25.2 degrees compared to Earth's 23.4. This means Mars has seasons, just like Earth, summers and winters. Spring thaws and autumn chills. The polar ice caps grow and shrink with the seasons, expanding in winter and retreating in summer, a slow, rhythmic breathing that you can watch from orbit. But that is where the similarities end, because the Martian environment is as hostile as it is familiar looking. The average surface temperature on Mars is minus 60 degrees Celsius. At the poles in winter, it drops below minus 125 degrees. The atmosphere is 95% carbon dioxide and exerts less than 1% of the pressure of Earth's atmosphere at sea level. If you stood on Mars without a spacesuit, three things would kill you almost simultaneously: the cold, the lack of oxygen, and the low pressure that would cause your blood to boil at body temperature. The surface is bathed in ultraviolet radiation that would sterilize any exposed organism within hours. And yet, this hostile, frozen, irradiated world was not always this way. And the story of how it changed, of how a planet that may have been more hospitable than early Earth became the most famous desert in the solar system, begins with chaos. 4.5 billion years ago, there was no Mars, there was no Earth, there was no Sun. There was only a vast, slowly rotating cloud of gas and dust drifting through a quiet arm of the Milky Way galaxy. This cloud was mostly hydrogen and helium, the simplest elements in the universe, but scattered through it were heavier atoms forged in the cores of stars that had lived and died long before. Iron, silicon, oxygen, carbon, the raw materials of rocky worlds. Something disturbed this cloud, perhaps a shock wave from a nearby supernova, perhaps the gravitational tug of a passing star. We are not entirely sure, but the disturbance caused the cloud to begin collapsing inward. As it contracted, it spun faster, flattening into a disk. At the center, temperatures and pressures climbed until hydrogen atoms began fusing together. The sun ignited. But the disk did not disappear. It remained spinning around the newborn star, and within it, a process began that would take tens of millions of years to complete. Tiny grains of dust began sticking together. Pebbles formed, then boulders, then objects kilometers across, called planetesimals. These planetesimals collided, shattered, reformed, and collided again in a violent cascade of impacts that slowly built larger and larger bodies. In the inner solar system, where temperatures were high enough to drive away most volatile gases, the worlds that formed were rocky. Mercury, Venus, Earth, and Mars. But here is the first thing most people do not know about Mars. It formed fast, unbelievably fast. While Earth took somewhere between 50 and 100 million years to reach its final size, Mars was essentially finished within the first 10 million years of the solar system. We know this because of isotopic analysis of Martian meteorites, rocks blasted off the surface of Mars by ancient impacts that eventually fell to Earth. The ratios of certain isotopes in these meteorites tell us that Mars differentiated, meaning its iron sank to the center to form a core, while lighter rock rose to the surface within just 4 million years of the solar system's birth. This means Mars is, in a sense, a relic, a fossil planet. It is what a rocky world looks like when it forms quickly and then, for reasons we will explore tonight, stops growing. Earth continued to accumulate mass through a long series of giant impacts, the last and most dramatic being the collision with a Mars-sized body called Theia that created our moon. Mars never experienced that kind of late-stage growth. It reached about 11% of Earth's mass and then stopped. Why did Mars stop growing? The answer lies in the gravitational architecture of the early solar system. Mars formed in a region sandwiched between the massive gravitational influence of Jupiter, which was already forming as a gas giant, and the growing proto-Earth. Jupiter's gravity stirred up the planetesimals in Mars's feeding zone, increasing their velocities to the point where collisions were more likely to shatter bodies than to merge them. Mars was starved. The material it needed to grow was either scattered by Jupiter or swept up by Earth, leaving Mars as the runt of the inner solar system. Recent computer simulations of solar system formation, the so-called Grand TAC model, suggest that Jupiter may have migrated inward and then back outward during the first few million years, sweeping through the region where Mars was forming and scattering the building blocks that Mars needed. Without Jupiter's interference, Mars might have grown to the size of Earth or larger. The solar system's largest planet may have inadvertently killed its smallest neighbor before that neighbor ever had a chance. And that small size would turn out to be the most important fact about Mars. It would determine everything that followed: the planet's brief golden age, its magnetic field, its atmosphere, its oceans, and ultimately its death. Because Mars was too small. Too small to hold onto the heat it needed. Too small to sustain the geological engine that could have saved it. A world that was born with everything it needed for life, but lacked the one thing that could have preserved it: mass. But we are getting ahead of ourselves, because before Mars died, it lived. And the evidence of that life, geological life at least, is written across its surface in features so dramatic that they stunned scientists when they first saw them. Let us talk about the water. In the early 1970s, when NASA's Mariner 9 became the first spacecraft to orbit another planet, it arrived at Mars during a global dust storm. For weeks, the cameras saw nothing but a featureless haze. Scientists waited, and when the dust finally began to settle, the first features to emerge above the murk were the peaks of enormous volcanoes. Then, as the atmosphere continued to clear, something else appeared: channels, vast, branching, sinuous channels carved into the Martian surface, stretching for hundreds of kilometers. They looked exactly like dry riverbeds. This was, at the time, shocking. Mars was supposed to be a dead, moon-like world. The Mariner 4 flyby in 1965 had returned images of a cratered surface that looked lifeless and ancient. But Mariner 9 revealed a planet of staggering geological complexity. Not just channels, but canyons, layered terrain, polar ice caps, and signs of erosion everywhere. Something had carved those channels. Something had shaped that landscape. And the most obvious explanation was water. Over the decades that followed, the evidence mounted. Orbital images from the Mars Global Surveyor, Mars Express, and the Mars Reconnaissance Orbiter revealed features that could only have been created by flowing liquid water. Not just small streams, but catastrophic floods, outflow channels tens of kilometers wide that erupted from underground sources and carved their way across the surface with a force that makes the largest floods on Earth look trivial. The most dramatic of these channels is a region called Cheyava Falls. It stretches for nearly 3,000 kilometers across the Martian surface, and at its widest, it is over 400 kilometers across. The volume of water that carved this channel is estimated to have been comparable to the combined flow of all rivers on Earth at once. These were not gentle streams, they were planetary-scale deluges, events so violent they reshaped entire regions in days or weeks. But the floods were not the whole story. In 2015, data from NASA's MAVEN orbiter, combined with measurements from the Mars Express spacecraft, allowed scientists to reconstruct the history of water on Mars with unprecedented detail. And the picture that emerged was far more dramatic than anyone had expected. During the Noahian period, roughly 4.1 to 3.7 billion years ago, Mars had enough water to cover its entire surface in a global ocean, approximately 137 meters deep. But that water was not evenly distributed. Mars, like Earth, has a dramatic difference in elevation between its northern and southern hemispheres. The northern lowlands sit several kilometers below the southern highlands, and most of that water would have pooled in the north, creating an ocean that covered nearly a third of the planet's surface, with depths reaching over a kilometer in places. Think about that for a moment. A Martian ocean. An actual ocean, with a shoreline you could have walked along, with waves driven by wind under a thick atmosphere, with sediment carried by rivers that flowed from the southern highlands down into the northern basin. An ocean that existed for hundreds of millions of years. And the evidence goes even deeper than we thought. In 2024, researchers at the Chinese Academy of Sciences published an analysis of data from China's Zhurong rover, which landed in Mars's Utopia Planitia in 2021. The rover's ground-penetrating radar detected layered sedimentary structures beneath the surface that are consistent with marine deposits, the kind of layered rock you find at the bottom of an ocean. Combined with chemical analysis of surface rocks showing salt deposits and minerals that only form in the presence of water, the evidence for a northern Martian ocean has become difficult to dismiss. But here is the question that haunted scientists for decades. If Mars once had all this water, oceans and rivers and lakes and rain, where did it all go? The answer to that question is one of the most dramatic stories in planetary science. It is a story about a planetary catastrophe that unfolded over hundreds of millions of years. Slow enough that no single generation would have noticed, but fast enough to turn a living world into a frozen desert. And it all started with something deep inside Mars that stopped working. This is shocking discovery number 1. The death of Mars was not caused by an asteroid impact, or a massive volcanic eruption, or some external cataclysm. It was caused by something far more fundamental. Mars's heart stopped beating. Every rocky planet generates heat in its interior through two main processes: the residual heat left over from its formation, the energy of all those impacts that built the planet, and the ongoing decay of radioactive elements like uranium, thorium, and potassium in the mantle and core. This internal heat drives convection in the liquid iron outer core, and that convection generates a magnetic field through a process called dynamo action. Earth has a powerful magnetic field. You have felt its effects every time you have used a compass. It extends tens of thousands of kilometers into space, creating an invisible shield called the magnetosphere that deflects the solar wind, the constant stream of charged particles flowing outward from the sun. Without this magnetic shield, the solar wind would interact directly with our atmosphere, slowly stripping it away molecule by molecule. Mars once had a magnetic field too. We know this because of the Mars Global Surveyor, which mapped the Martian magnetic field from orbit in the late 1990s and found something remarkable. While Mars today has no global magnetic field, it does have intense patches of magnetism embedded in its oldest crustal rocks in the southern highlands that formed more than 4 billion years ago. These magnetic anomalies are the fossilized remnants of an ancient global field, preserved in the rock like a recording of a song that stopped playing long ago. The strength of these crustal magnetic fields is extraordinary. In some places, 10 to 20 times stronger than anything found on Earth's surface. This tells us that when Mars had a global magnetic field, it was powerful, perhaps even more powerful than Earth's field today. Mars was, for a time, magnetically protected. And then, sometime around 4 billion years ago, the field collapsed. The exact mechanism is still debated, but the most widely accepted explanation is straightforward and devastating. Mars was simply too small. With only about 11% of Earth's mass, Mars had less radioactive material to generate heat and a larger surface area to volume ratio that allowed it to cool faster. Over hundreds of millions of years, the interior of Mars cooled enough that convection in the liquid iron core slowed and eventually stopped. Without convection, the dynamo died. Without the dynamo, the magnetic field faded. And without the magnetic field, Mars was naked. The solar wind, which had been deflected harmlessly around the planet for hundreds of millions of years, now had direct access to the upper atmosphere. Charged particles from the sun slammed into atmospheric molecules, transferring enough energy to accelerate them to escape velocity. One by one, molecule by molecule, the atmosphere began to bleed away into space. This process is called sputtering, and NASA's MAVEN orbiter has measured it happening in real time. Even today, 4 billion years after the magnetic field collapsed, Mars is still losing atmosphere. MAVEN has measured the rate, about 100 grams of atmosphere escaping every second. That sounds small, but over 4 billion years, it adds up to an extraordinary amount of gas. Scientists estimate that Mars has lost between 60 and 90% of its original atmosphere through this process. And as the atmosphere thinned, everything else began to unravel. Atmospheric pressure dropped. On Earth, water boils at 100 degrees Celsius because our atmosphere exerts enough pressure to keep it liquid at that temperature. But if you reduce the atmospheric pressure enough, water can boil at much lower temperatures, even at 0 degrees Celsius. As Mars's atmosphere thinned, the surface pressure eventually dropped below the point where liquid water could exist stably. Water began to evaporate, not into clouds that would rain back down, but directly into the thinning atmosphere, where it too was stripped away by the solar wind. Some of the water froze. It retreated to the polar caps, or seeped into the ground, or was trapped in mineral deposits. But much of it was simply lost to space, broken apart by ultraviolet radiation into hydrogen and oxygen, with the lightweight hydrogen escaping the planet's gravity and the oxygen either escaping or being locked into the iron-rich surface rocks, which is, incidentally, why Mars is red. The rust color of Mars is literally the oxygen from its ancient oceans bonded to iron in the soil. The process was not uniform. It was punctuated by periods of more intense stripping, driven by solar storms and coronal mass ejections. The young sun was far more active than it is today. It rotated faster, produced stronger magnetic fields, and unleashed solar flares and coronal mass ejections hundreds of times more powerful than anything we observe now. Each major solar storm would have blasted away chunks of the Martian atmosphere in bursts, accelerating the process of erosion. Maven has observed this happening in real time during modern solar storms. In March 2015, a moderate solar storm hit Mars, and Maven measured the atmospheric escape rate spike to 10 times the normal level. If modern, relatively mild solar storms can do that, imagine what the violent solar storms of 4 billion years ago did to a Mars that had already lost its magnetic shield. The atmosphere was being sandblasted away. The Martian sky changed too. On Earth, our atmosphere scatters blue light, giving us blue skies. Mars's atmosphere is so thin that it scatters light differently. The daytime sky on Mars is a butterscotch color, and sunsets are blue. It is an inverted Earth, a mirror world where everything is backwards. The whole process, from a warm, wet planet with a thick atmosphere and a magnetic shield to a cold, dry desert with an atmosphere less than 1% the density of Earth's, took somewhere between 500 million and 1 billion years. In geological terms, this is fast. Mars went from habitable to hostile in what amounts to a blink of cosmic time. And that brings us to one of the most tantalizing questions in all of science. During those hundreds of millions of years when Mars had warm oceans, a thick atmosphere, and all the chemical ingredients necessary for biology, did life emerge? Because if life arose on Mars during its wet period, the implications are staggering. It would mean that life is not a one-time miracle that happened only on Earth. It would mean that wherever conditions are right, life finds a way. It would transform our understanding of our place in the universe. And the search for the answer to that question is one of the greatest detective stories ever told. It begins with 2 spacecraft that landed on Mars in 1976, and an experiment whose results have haunted scientists for half a century. This is shocking discovery number 2. In 1976, NASA did something extraordinary, something we have never done before or since. They sent 2 spacecraft to Mars, Viking 1 and Viking 2, each equipped with a robotic arm, a miniature chemistry laboratory, and 3 experiments specifically designed to detect life. Think about that for a moment. Half a century ago, we had robots on the surface of Mars conducting biology experiments. The ambition of it still takes your breath away. The Viking landers were technological marvels of their era. Each one weighed over 600 kilograms on the surface, massive by any standard, even today. They carried cameras, weather stations, seismometers, and those 3 biology experiments: the gas exchange experiment, the pyrolytic release experiment, and the labeled release experiment. The gas exchange experiment took a sample of Martian soil, added water and nutrients, and looked for changes in the gases above the soil. If microorganisms were present, they would metabolize the nutrients and release or absorb gases, just as bacteria on Earth do. The pyrolytic release experiment tried to detect photosynthesis or chemical fixation of carbon. It exposed soil to radioactively labeled carbon dioxide and carbon monoxide, then heated the sample to see if any of the labeled carbon had been incorporated into organic molecules, a sign that something in the soil was actively using carbon. And the labeled release experiment, the one that would become the most controversial, worked like this. A small sample of Martian soil was moistened with a nutrient solution containing radioactively labeled carbon compounds. If any organisms in the soil metabolized those nutrients, they would release radioactive carbon dioxide gas, which the instrument could detect. Here is what happened. The gas exchange experiment produced ambiguous results. There was a burst of oxygen when the soil was moistened, but it was likely caused by chemical reactions with peroxides in the soil rather than biological activity. The pyrolytic release experiment gave weakly positive results in some runs and negative results in others. Inconclusive, but the labeled release experiment gave a strong, unambiguous positive result. When the nutrient solution was added to the Martian soil, the instrument detected a clear release of radioactive gas. The signal looked exactly like what you would see if you ran the same experiment with soil from Earth containing bacteria. The scientists were stunned. The experiment had worked. It had detected something. But then came the control. In the experimental protocol, after getting a positive result, you sterilize the soil by heating it to 160 degrees Celsius, hot enough to kill any known microorganism, and then repeat the experiment. If the positive result was biological, the sterilized soil should show no activity. If it was chemical, the result might persist even after heating. The sterilized soil showed no activity. The signal disappeared. This was exactly what you would expect if the initial positive result was caused by living organisms that were killed by the heat. So the Viking labeled release experiment got a positive result, and the control experiment confirmed it in exactly the way biology would predict. By the criteria the scientists had established before the mission, this was a detection of life on Mars. But there was a problem, a big problem. Another instrument on the Viking landers, the gas chromatograph mass spectrometer, or GCMS, was designed to detect organic molecules in the Martian soil. Organic molecules are the building blocks of life as we know it. Every living thing on Earth is made of organic molecules. If there were microorganisms in the Martian soil producing the labeled release signal, there should have been organic molecules detectable by the GCMS. The GCMS found none. Zero. Not a single organic molecule at the detection limit of the instrument, which was a few parts per billion. This created an impossible paradox. One experiment said, yes, life is here. Another experiment said, no, there is not even organic chemistry happening. The two results seem to contradict each other directly. The scientific community, after years of debate, eventually sided with the GCMS. The consensus became that the labeled release results were caused by some unknown chemical reaction, perhaps involving reactive peroxides or superoxides in the Martian soil that could mimic biological activity. The Viking mission was officially declared to have found no evidence of life on Mars. But Gilbert Levin, the principal investigator of the labeled release experiment, never accepted that conclusion. For the rest of his life, he continued publishing papers into his 90s. Levin argued that his experiment had detected life on Mars and that the scientific community had made a grave error in dismissing the results. He pointed out that no one has ever been able to produce the exact Viking LR results using any known non-biological chemistry. Levin was not a crank or a fringe scientist. He was a highly respected researcher who had spent years designing an experiment that was vetted and approved by NASA's own review panels. The labeled release experiment performed exactly as designed, met all its pre-established criteria for a positive result, and was rejected not because of any flaw in the experiment itself, but because of a contradiction with a different instrument. Levin spent the remaining decades of his career. He passed away in 2021 at the age of 97, arguing that history would vindicate him. Whether it will or not remains to be seen, but the evidence that has accumulated since 1976 has consistently moved in his direction. And here is the twist that makes this story even more remarkable. In the decades since Viking, we have learned things about the GCMS that change everything. First, we now know that the Martian soil is bathed in perchlorate, a highly oxidizing chemical compound that was first detected by the Phoenix lander in 2008. Perchlorates are reactive. When heated, as the GCMS heated its soil samples, perchlorates can destroy organic molecules, breaking them down into chlorinated compounds that the Viking GCMS was not designed to detect. In other words, the very process of analyzing the soil may have destroyed the evidence the instrument was looking for. Second, in 2018, NASA's Curiosity rover detected organic molecules in Martian rocks, definitively proving that organic chemistry does exist on Mars. The GCMS did not find organics not because they were absent, but because the instrument was not sensitive enough and the perchlorates were actively destroying the very molecules it was searching for. This means the entire basis for rejecting the labeled release results, the absence of organics, has collapsed. The foundation of the scientific consensus that Viking did not find life has been pulled out from under it. Does this mean Viking found life? We still do not know for certain. The debate continues. But the question is no longer closed. It is very much open. And it is one of the most extraordinary unresolved questions in the history of science. There is one more detail about the Viking story that most people do not know. A detail that adds another layer of complexity to an already tangled tale. In 2012, a team of researchers reanalyzed the original Viking LR data using a mathematical technique called complexity analysis. They compared the patterns in the Viking data to patterns produced by biological systems and patterns produced by purely chemical reactions. Their conclusion: the Viking LR data showed a degree of complexity more consistent with biological processes than with simple chemistry. The patterns were not random. They were not what you would expect from a sterile chemical reaction. They had a structure, a mathematical signature that looked like life. This study did not prove that Viking found life. No single study could. But it added another thread to a web of evidence that continues to grow more tangled and more fascinating with each passing year. Now, before we continue deeper into the Mars story, let us pause for a moment and appreciate something about the way science works. Because the Viking story is not just about Mars, it is about the way human beings handle evidence that does not fit their expectations. In 1976, the scientific community was presented with a clear positive result from a carefully designed life detection experiment. The result met all the pre-established criteria for a positive detection. But it was rejected, not because the experiment was flawed, but because another instrument failed to find what scientists expected to find alongside it. And that rejection held for decades, shaping the direction of Mars exploration influencing which missions were funded and which were not, determining which questions were asked and which were avoided. It took 40 years of additional discoveries, perchlorates, organic molecules, a complete rethinking of Martian chemistry to reopen the question. 40 years, an entire generation of scientists lived and retired in the shadow of a conclusion that may have been wrong. This is not a criticism of science, it is a feature. Science is conservative by nature. It demands overwhelming evidence before accepting extraordinary claims, and that conservatism protects us from countless errors. But sometimes, rarely, that conservatism also causes us to overlook truths that are staring us in the face. The Viking story is a reminder that the absence of evidence is not evidence of absence, and that the most important discoveries sometimes hide in the gaps between what our instruments can measure. Now, let us jump forward in time. Because while scientists on Earth were debating the Viking results, Mars was waiting. And in 2004, 2 small robots arrived that would change everything we knew about Martian geology and reopen the question of water in a way that no one could dismiss. This is where we meet Spirit and Opportunity. The Mars exploration rovers, Spirit and Opportunity, landed on Mars in January 2004, 3 weeks apart. They were designed for 90-day missions. Between them, they would operate for more than 20 years. Spirit landed in Jezero Crater, a large impact basin that scientists believed had once been filled by a lake fed by an enormous outflow channel called Maadim Vallis. The hope was that Spirit would find sedimentary rocks, lake deposits, that would prove water had once filled the crater. Opportunity landed on the other side of the planet in a small crater on the flat plain of Meridiani Plenum. The landing site was chosen because orbital data had detected the spectral signature of a mineral called gray hematite, a form of iron oxide that on Earth almost always forms in the presence of water. Both rovers were equipped with cameras, spectrometers, a rock abrasion tool for grinding into rocks, and a microscopic imager that could photograph rock textures at scales smaller than a millimeter. They were, in essence, robotic geologists. Spirit had a difficult start. Jezero Crater turned out to be covered in volcanic basalt, lava flows that had buried whatever lake sediments might lie beneath. For months, Spirit drove across a plain of unremarkable volcanic rock, finding no clear evidence of water. Scientists began to wonder if they had chosen the wrong landing site. But then Spirit reached the Columbia Hills, a low range of hills about 3 kilometers from its landing site, and everything changed. The rocks in the Columbia Hills were completely different from the volcanic plains. They were layered, altered, transformed by water. Spirit found minerals that only form in hot water. Goethite, hematite, sulfates. It found rocks that had been chemically weathered in ways that require prolonged contact with liquid water. The Columbia Hills told a story of ancient hydrothermal activity. Hot springs, perhaps, or groundwater seeping through volcanic rock. Mars had been wet here, intensely wet. But it was opportunity that delivered the knockout punch. Within weeks of landing, Opportunity made one of the most important geological discoveries in the history of planetary exploration. In the walls of the small crater where it landed, the rover found exposed layers of sedimentary rock containing tiny spherical objects embedded in the stone. Scientists nicknamed them blueberries because of their small, round shape. Chemical analysis revealed they were made of hematite, the same mineral that had been detected from orbit. But the real revelation came from the sedimentary rock itself. Under the microscopic imager, the rock showed a texture called cross-bedding. layers of sediment deposited at angles to each other, created by flowing water or wind. More importantly, Opportunity found tabular crystal voids in the rock, molds left behind by crystals that had formed in the rock and later dissolved. The shape and distribution of these voids were consistent with minerals that form when standing water slowly evaporates, like the patterns you see when a salt lake dries up. Opportunity had landed on the shore of an ancient body of standing water. This was not a catastrophic flood or a brief episode of dampness. This was a persistent body of water, a shallow, salty sea that had existed long enough to leave its signature in layers of sedimentary rock. Their discovery electrified the scientific community. For the first time, we had direct, ground truth evidence of a persistent body of standing water on Mars. Not inferred from orbital images, not modeled from chemical data, but physically present in the rock record, readable like a page from a geology textbook. The sedimentary structures were so clear, so unmistakable, that even the most cautious scientist acknowledged the evidence was overwhelming. Opportunity also discovered something else in the Meridiani rocks, jaruste. This mineral is a potassium iron sulfate that only forms in acidic water. Its presence told scientists that the ancient Meridiani water was not a freshwater lake, but an acidic, briny pool, hostile to many forms of life, but not to all. On Earth, extremophile organisms, called acidophiles, thrive in similarly harsh conditions. The acid mine drainage of abandoned coal mines, the sulfuric hot springs of Yellowstone, the iron-rich rivers of the Rio Tinto in Spain. All are acidic environments teeming with microbial life. The water at Meridiani was unpleasant by human standards, but perfectly acceptable by the standards of Earth's toughest microbes. And Opportunity was just getting started. Over the next 15 years, yes, 15 years, from a rover designed for 90 days, Opportunity drove more than 45 kilometers across the Martian surface, visiting crater after crater, each one exposing deeper and older layers of rock. And everywhere it looked, it found the same story: water. Ancient, persistent, widespread water. Hot endurance crater. Opportunity found meters of layered sulfate-rich rock, evidence of a water body that had grown and shrunk repeatedly over time, like a lake in a climate that oscillated between wet and dry periods. At Victoria Crater, it found even deeper exposures of the same water-altered rocks, extending the timeline further into the past. And at Endeavour Crater, a massive, ancient impact basin 22 kilometers across, Opportunity found clay minerals that form only in water with a neutral pH. Not acidic, not caustic, but the kind of water you could drink. The kind of water that life as we know it thrives in. Opportunity's journey ended in June 2018 when a global dust storm, one of the most intense ever observed on Mars, blocked so much sunlight that the solar-powered rover could no longer charge its batteries. NASA sent over 1,000 commands to Opportunity, trying to wake it up. For months, they tried. The final command was sent on February 12, 2019. Opportunity never responded. The last message from Opportunity, translated from the data it sent as the dust storm closed in, has become one of the most poignant moments in space exploration. My battery is low and it is getting dark. That was how Opportunity died. Slowly, in the dark, on a planet it had explored for over 5,000 Martian days, having traveled farther than any other vehicle on the surface of another world. It arrived expecting to last 90 days and survived for nearly 15 years. In that time, it fundamentally proved that Mars was once a wet world. Not just briefly, not just locally, but persistently and globally. Spirit had its own remarkable end. In 2009, the rover became stuck in soft soil at a site called Troy. Despite months of effort, engineers could not free it. Spirit became a stationary science platform, studying the soil and atmosphere from its fixed position. Communication was lost in March 2010. Spirit had operated for over 6 years, more than 25 times its designed lifetime. Together, Spirit and Opportunity transformed our understanding of Mars. They proved that Mars had sustained liquid water on its surface for extended periods. They found minerals that require water to form. They found sedimentary rocks deposited by standing water. They found evidence of hydrothermal systems. They gave us a Mars that was not just wet, but habitable. A world where, if life had emerged, the conditions existed for it to survive. And that legacy led directly to the next chapter in our story. A chapter that is still unfolding right now, as we speak, in an ancient crater that may hold the most important rocks in the solar system. This is shocking discovery number 3. Let us talk about Jezero Crater. Jezero Crater is a 49-kilometer wide impact basin in the northern hemisphere of Mars, just north of the equator. From orbit, it is one of the most geologically stunning sites on the planet. On its western rim, a dried river channel cuts through the crater wall and fans out into a broad, flat deposit inside the crater. This is a delta, the same kind of sedimentary formation you find where rivers meet lakes or oceans on Earth. The Nile Delta, the Mississippi Delta, the Ganges Delta. Jezero's delta formed billions of years ago, when a river carried sediment into a crater lake that may have existed for millions of years. The delta is beautifully preserved. You can see individual layers in orbital images, stacked one on top of another, recording the history of that lake in sedimentary detail. It is, quite possibly, the best preserved ancient delta in the solar system. This is why NASA chose Jezero as the landing site for its most ambitious Mars rover yet. In February 2021, the Perseverance rover touched down on the crater floor, about 2 kilometers from the base of the delta. Its primary mission, to search for signs of ancient microbial life and to collect rock samples that will eventually be returned to Earth. The choice of Jezero was not made lightly. It was the result of years of debate among scientists, with dozens of candidate sites evaluated for their scientific potential, safety, and accessibility. Some scientists argued for Jezero Crater, where Spirit had found evidence of hot springs. Others pushed for Mount Vallis, a region rich in clay minerals that might preserve ancient biosignatures. Still others advocated for the northeast Syrtis region, where deep crustal rocks exposed by erosion could provide a window into Mars's earliest and most potentially habitable periods. Jezero won because it offered something no other site could match: a well-preserved ancient delta that combined multiple environments in a single location. The crater floor provided igneous rocks that could be dated precisely. The delta provided sedimentary rocks deposited by flowing water, and the rocks above the delta recorded the transition from wet to dry, the death of the lake and the beginning of the arid era that continues today. Jezero was, in geological terms, a one-stop shop for understanding the history of water and habitability on Mars. Perseverance is not like any rover that came before it. It carries 23 cameras, 2 microphones, the first to record actual sounds on Mars, a helicopter drone called Ingenuity, a suite of instruments designed to analyze rock chemistry at microscopic scales, and a system for drilling rock cores and sealing them in titanium tubes for future collection. In its first year, Perseverance explored the crater floor, analyzing igneous rocks that turned out to have been altered by water, soaked essentially in liquid that permeated the rock and changed its chemistry long after it formed. The rover found olivine and pyroxene minerals that had been partially transformed into carbonates and sulfates, telltale signs of prolonged water interaction. But the real excitement began when Perseverance reached the delta. Climbing up the sedimentary layers of the Jezero Delta was like reading a book written in stone. Each layer a page, each mineral a word. The rover found mudstones, fine-grained sedimentary rocks formed from clay and silt deposited in quiet, standing water. It found sandstones, coarser deposits laid down by flowing water carrying heavier particles. It found conglomerates, rocks made of rounded pebbles cemented together, evidence of fast-moving streams that tumbled rocks smooth. And then, in July 2024, Perseverance drilled into a rock that would make headlines around the world. The rock was called Cheyava Falls, named after a waterfall in the Grand Canyon. It was a mudstone from the ancient delta, a rock that formed at the bottom of the Jezero Lake billions of years ago. When Perseverance analyzed it with its hairlock and pixel instruments, specialized spectrometers that can map the chemical composition of a rock at millimeter scales, the results were unlike anything seen before on Mars. The rock contained irregular patches of iron phosphate arranged in a distinctive leopard-spot pattern. On Earth, this specific texture, alternating light and dark spots of iron and phosphate minerals, is a well-known biosignature. It is produced by microorganisms that metabolize iron compounds, creating distinctive chemical patterns in the rock as they grow and die. This texture has been found in ancient rocks on Earth dating back billions of years, and in every known case, it is biological in origin. But that was not all. Threaded through the leopard spots, Perseverance detected veins of organic carbon, the element that forms the backbone of all known life. The organic material was concentrated in specific zones within the rock, associated with the iron phosphate textures, in a way that suggested it was not randomly distributed, but structurally related to the mineral patterns. When the results were announced in September 2025, the scientific community reacted with a mixture of excitement and extreme caution. NASA's official statement was carefully worded. The Cheyava Falls rock contained features that were consistent with biosignatures but could potentially be explained by non-biological processes. The rock could be a sign of ancient life, or it could be the product of unusual chemistry that happened to mimic biological patterns. This careful language is important, and it tells us something about the stakes involved. A confirmed detection of past life on Mars would be one of the most significant scientific discoveries in human history. It would mean that life arose independently on two separate planets in the same solar system, suggesting that the emergence of life is not a freak accident, but a natural, perhaps inevitable, consequence of the right conditions. The implications for the prevalence of life in the universe would be profound. Because of those stakes, scientists are holding their judgment. The Cheyava Falls rock needs to be studied in laboratories on Earth, with instruments far more powerful and sensitive than anything a rover can carry. It needs to be analyzed for specific biomolecular signatures, amino acids, lipids, nucleic acids, that would conclusively distinguish biological from non-biological origins. And that is why the Mars sample return mission matters so much. Perseverance has been collecting rock cores and sealing them in tubes some cached on the Martian surface, others stored inside the rover. These tubes contain what might be the most scientifically valuable rocks in the solar system. Getting them back to Earth is the next great challenge. But the Mars Sample Return mission is in trouble. Originally planned as a collaboration between NASA and the European Space Agency, the mission has been delayed repeatedly and its budget has ballooned to over $11 billion. By 2003, the original architecture, which involved a complex sequence of a lander, a Mars ascent vehicle, an orbiter, and an Earth entry vehicle, was deemed too expensive and too risky. NASA announced it was seeking alternative approaches. As of ET26, the future of Mars sample return remains uncertain. Several proposals are under consideration, including simpler mission architectures and potential commercial partnerships. But the fundamental challenge remains: getting a rocket to launch from the surface of Mars, rendezvous with a spacecraft in orbit, transfer the sample tubes, and fly them back to Earth is one of the most technically demanding operations ever contemplated in spaceflight. The irony is painful. We may have the most important rocks in the history of science sitting on the surface of Mars, inside sealed titanium tubes, waiting to tell us whether life ever existed beyond Earth, and we cannot get them home. Not yet. But the scientific community is working on it, because the answer to the question those rocks might hold is worth whatever it takes to retrieve them. Now, while Perseverance has been exploring Jezero Crater, another rover has been making discoveries of its own on the other side of the planet, and what it found in 2026 may be just as significant as Cheyava Falls. This is shocking discovery number 4. Let us talk about Curiosity. The Curiosity rover landed in Gale Crater in August 2012. As of 2026, it has been operating on Mars for more than 14 years, more than 5,000 Martian days. It has driven over 32 kilometers across the crater floor and up the lower slopes of Mount Sharp, a 5-kilometer high mound of layered sedimentary rock in the center of the crater. Mount Sharp is a geological library. Each layer records a different chapter of Martian history, and Curiosity has been reading those chapters one by one as it climbs. From its earliest days, Curiosity made discoveries that reshaped our understanding of Mars. In its minor teens, it found mudstones in an area called Yellowknife Bay that contained clay minerals, sulfur compounds, and the elements carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, all the key ingredients for life. The analysis showed that Gale Crater once contained a lake of fresh, drinkable water with a neutral pH, not toxic, not ultra-acidic, not hypersaline, but the kind of water that life on Earth thrives in. NASA announced that Gale Crater had been habitable. But Gale Crater's story goes deeper. As Curiosity climbed the lower slopes of Mount Sharp, it passed through layers of rock that recorded a changing environment. The lowest layers, the oldest, were mudstones from a lake. Above those, sandstones indicated a transition to a drier environment with intermittent streams. Higher still, sulfate-rich rocks spoke of a world where water was evaporating, leaving behind concentrated mineral deposits. Mount Sharp is a geological archive, and Curiosity is reading it from bottom to top, chapter by chapter, watching Mars dry out in slow motion. The story these rocks tell is not a simple one of gradual drying. Instead, they reveal oscillations, periods of wet conditions, alternating with dry periods, suggesting that Mars's climate flickered between habitable and inhospitable states before the final drying. These climate oscillations may have lasted hundreds of millions of years, and they raise a profound question. If life emerged during the wet periods, could it have survived the dry intervals by retreating underground or entering dormancy? On Earth, some bacteria can form spores that survive for millions of years, reactivating when conditions improve. If Martian microbes had similar capabilities, they could have persisted through the climate oscillations, waiting for the next wet period, a period that eventually never came. In 2004, Curiosity detected a sudden spike in methane levels in the Martian atmosphere, 10 times higher than the background level. This was extraordinary because on Earth, the vast majority of atmospheric methane is produced by living organisms, microbes called methanogens, that thrive in oxygen-free environments like swamps, rice paddies, and the digestive systems of cattle. Could Martian methane be biological? The methane story has only grown more mysterious since then. Curiosity has detected seasonal variations in Mars's background methane levels. They rise in summer and fall in winter, just as you might expect if the methane were being produced or released by a process tied to temperature. But the amount of methane is tiny, parts per billion, and there are potential non-biological explanations, including the interaction of water with olivine minerals through a process called serpentinization, or the UV degradation of organic material deposited by meteorites. What makes the methane mystery particularly maddening is that ESA's Trace Gas Orbiter, which was specifically designed to detect methane from orbit, has not confirmed Curiosity's surface-level detections. This suggests that the methane is being produced locally and destroyed or dispersed before it can spread through the atmosphere. Something on Mars is producing methane and something else is destroying it. We do not know what either process is. But the most remarkable of Curiosity's discoveries came in 2026, and it is one that has received far less public attention than it deserves. In early 2026, the Curiosity team announced the detection of the most complex organic molecules ever found on Mars, using the rover's sample analysis at Mars Instrument, SAM, a miniature chemistry laboratory that can heat rock samples and analyze the gases they release. The team identified long-chain organic molecules with structures that closely resemble those found in biological systems on Earth. These were not simple organic compounds, not the basic chlorinated hydrocarbons that had been detected in earlier analyses. These were complex, multi-carbon molecules with branching structures and functional groups that, on Earth, are typically associated with biological processes. The specific structures have not been fully published as of mid-2026, as the analysis is still ongoing, but preliminary reports indicate they include the longest carbon chains ever detected on another planet. Now, finding complex organic molecules does not prove life exists or existed on Mars. Organic molecules can form through non-biological processes. They have been found in meteorites, in interstellar gas clouds, and even in the atmospheres of gas giant planets where no one suggests life is present. The question is not whether organic molecules exist on Mars, but whether the specific types of organic molecules found there are more consistent with biological or non-biological origins. On that question, like so many questions about Mars, awaits the return of those samples to Earth. But let us step back for a moment and consider what we have learned so far. Mars once had oceans and a thick atmosphere. It had a magnetic field that protected it. It lost all of these things when its core cooled and the solar wind stripped its atmosphere away. During its wet period, which lasted hundreds of millions of years, conditions on Mars were suitable for life. Viking may or may not have detected life in 1976. Perseverance has found rocks with patterns that look biological. Curiosity has found complex organic molecules and mysterious methane. And beneath the surface, there may still be liquid water. Let us talk about that water. Because the question of whether liquid water exists on Mars today, not in the past, but right now, is one of the most actively debated topics in planetary science. This is shocking discovery number 5. In 2018, a team of Italian scientists announced a discovery that made headlines around the world. Using data from the Marsis radar instrument on the European Space Agency's Mars Express orbiter, they reported detecting a bright radar reflection beneath the south polar ice cap of Mars at a depth of about 1.5 kilometers. The characteristics of the reflection, its brightness, and the way the radar signal behaved were consistent with a body of liquid water. The team published their findings in the journal Science, and the reaction was electric. Liquid water on Mars, not in the distant past, but now, today, trapped beneath the ice, kept liquid by the enormous pressure of the overlying ice cap, and possibly by dissolved salts that lower the freezing point. But as with everything on Mars, the story is more complicated than the headline suggests. Other scientists challenged the interpretation. Some argued that the radar signal could be explained by certain types of clay minerals or volcanic rock beneath the ice, which can also produce bright radar reflections. Others pointed out that for water to remain liquid at the temperatures found at the base of the Martian ice cap, around -68 degrees Celsius, it would need to contain extremely high concentrations of perchlorate salts. Water that salty would be so briny that it would be hostile to most forms of life as we know it, though some extremophile organisms on Earth can survive in similar conditions. In 2022, additional radar data seemed to weaken the liquid water hypothesis. A more comprehensive analysis of Mars's data found many bright reflections beneath the south polar cap, spread across a wide area, too many, some scientists argued, to all be liquid water. Some of these reflections came from areas where temperatures should be too cold for even the most salt-saturated brine to remain liquid. And yet, the debate continues. A Yendo 24 study using new analytical techniques on the Mars's data argued that at least some of the reflections are most consistent with liquid water and cannot be easily explained by alternative hypotheses. The Italian team that made the original discovery continues to defend their interpretation. The truth is, we do not yet have a definitive answer. Resolving this question will likely require a mission specifically designed to probe the Martian subsurface, perhaps a lander with a drill capable of penetrating kilometers of ice, or a network of seismic sensors that could detect the difference between liquid and solid beneath the surface. Such missions have been proposed, but none are currently funded. But here is why the question matters so much. If liquid water does exist beneath the Martian surface, it dramatically changes the prospects for finding life on Mars. Not ancient, fossilized life in billion-year-old rocks, but living organisms existing right now in dark, salty aquifers beneath the ice. On Earth, everywhere we find liquid water, we find life. In the deepest caves, in the hottest hydrothermal vents, in salt mines kilometers underground, in Antarctic ice sheets, in the acidic drainage of abandoned mines, everywhere. There is no known environment on Earth where liquid water exists and life does not. This is not proof that Mars's subsurface water, if it exists, harbors life. but it is a strong motivation to keep looking. And speaking of looking, let us turn our attention from the surface and the subsurface to the sky above Mars, because in 2026 we received confirmation of something in the Martian atmosphere that has been puzzling scientists for nearly 2 decades. The methane story we touched on earlier has taken a new twist. In early 2026, a joint analysis of data from Curiosity, the Trace Gas Orbiter, and ground-based telescopes produced the most detailed map yet of methane distribution on Mars. The analysis confirmed that methane is being emitted from specific regions of the Martian surface, not uniformly, but in localized plumes that appear and disappear over time. The pattern is striking. The methane emissions correlate with regions where orbital data suggests the presence of subsurface ice and where geological models predict the existence of water-rock interactions at depth. In other words, the methane is coming from exactly the places where you would expect it if it were being produced by either deep geological processes involving water or by living organisms. The correlation does not prove biology. Geological processes alone could explain the observations. But the seasonal variation, the localized emission, and the correlation with subsurface water all make the biological explanation surprisingly difficult to rule out. The methane mystery remains one of the most tantalizing unsolved puzzles in planetary science. Now let us shift our perspective entirely. We have been talking about the science of Mars, the geology, the chemistry, the search for life, but there is another dimension to the Mars story that deserves attention, the human dimension. The story of the people who have devoted their lives to exploring this planet and the extraordinary machines they have built to do it. Because the history of Mars exploration is not just a scientific triumph. It is a story of persistence in the face of failure. A story where more missions have failed than succeeded, where the margin between triumph and disaster has often been measured in centimeters, and where the determination of engineers and scientists has been tested again and again. Let us talk about the curse of Mars. In the early decades of space exploration, Mars earned a reputation as the most difficult destination in the solar system. Of the first 20 missions sent to Mars by various space agencies, only 7 succeeded. The failure rate was so high that engineers half-jokingly referred to a great galactic ghoul that devoured spacecraft on their way to the Red Planet. The Soviet Union bore the brunt of this curse. Between 1960 and 1973, the Soviets launched no fewer than 9 missions to Mars. Most failed at launch or during transit. Mars too reached the planet in 1971, but its lander crashed into the surface, becoming the first human-made object to reach Mars, but returning no data. Mars 3 achieved a soft landing, but transmitted for only 14.5 seconds before going silent. The images it returned were blank. The most heartbreaking Soviet failure came in 1996 when the Mars 96 mission, a sophisticated orbiter carrying multiple landers and penetrators, representing years of work and the hope of Russian planetary science, failed to leave Earth orbit. The rocket's upper stage malfunctioned and the spacecraft fell back into the atmosphere, crashing somewhere in the Pacific Ocean or possibly in the mountains of Bolivia. Years of work gone in minutes. NASA had its share of failures too. The Mars Observer, launched in 1992, was a $1 billion orbiter that was lost just 3 days before arriving at Mars. Contact was lost during a fuel pressurization maneuver. The spacecraft was never heard from again. To this day, no one knows exactly what went wrong. In 1999, NASA suffered 2 Mars failures in quick succession that became legendary cautionary tales. The Mars Climate Orbiter was lost because of a unit conversion error. One team had been using metric units while another used imperial, causing the spacecraft to fly too close to Mars and burn up in the atmosphere. 3 months later, the Mars Polar Lander crashed into the surface, likely because its descent engines shut off prematurely when the landing legs deployed and their vibration was misinterpreted by the software as contact with the ground. Test failures were devastating. They led to a complete restructuring of NASA's Mars program and the adoption of the faster, better, cheaper philosophy's successor, a more careful, methodical approach that prioritized reliability over ambition. And that approach paid off. Since 2001, NASA has achieved an extraordinary run of success at Mars. Mars Odyssey, which arrived in 2001, is still operating today, more than 25 years later. The Mars Reconnaissance Orbiter, which arrived in 2006, has returned more data than all other Mars missions combined. Spirit and Opportunity exceeded all expectations. Curiosity has been operating for over 14 years. Perseverance is actively collecting samples, and Maven continues to study the Martian atmosphere. Other space agencies have joined the Mars endeavor with increasing ambition. India's Mars Orbiter mission, Mangalyaan, reached Mars in 2014 on a shoestring budget of just $74 million, less than the cost of many Hollywood movies. It was India's first interplanetary mission, and it succeeded on the first attempt, a feat that neither the United States nor the Soviet Union achieved. The UAE's Hope Orbiter arrived at Mars in 2021, becoming the first Arab world interplanetary mission and delivering unprecedented observations of the Martian atmosphere and weather systems. China's Tianwen-1 mission, also arriving in 2021, included an orbiter, a lander, and the Zhurong rover, making China only the second country to successfully operate a rover on Mars. The international character of Mars exploration is one of its most remarkable features. In a world often divided by politics and competition, Mars has become a shared endeavor. Data from European orbiters complements observations by American rovers. Indian spacecraft relay signals for NASA missions. Chinese ground-penetrating radar data informs European geological models. Mars, in a very real sense, belongs to everyone. But the most dramatic success story of all, the one that best captures the audacity and brilliance of Mars exploration, is the landing of Curiosity in 2012. Because the method NASA used to put Curiosity on the surface of Mars was so outrageous, so seemingly impossible, that even the engineers who designed it called it 7 minutes of terror. Curiosity was too heavy for airbags, the bouncing ball landing method that had worked for Spirit and Opportunity, and a traditional propulsive landing where the spacecraft fires its engines all the way to the surface would kick up enormous clouds of dust and debris that could damage the rover's instruments. So the engineers invented something new, something that had never been tried before in the history of spaceflight. Here is how it worked. The spacecraft entered the Martian atmosphere at over 20,000 kilometers per hour, protected by a heat shield that absorbed temperatures over 2,000 degrees Celsius. A supersonic parachute deployed, slowing the descent. Then the heat shield was jettisoned, exposing the rover and its landing system. And then, still hundreds of meters above the surface and still moving too fast to land safely, the rover separated from the parachute and fired 8 retro rockets, not attached to the rover itself, but to a platform above it called the Sky Crane. The Sky Crane hovered in mid-air above the Martian surface, held aloft by its rockets, and lowered Curiosity on 3 nylon cables, like a spider lowering itself on silk threads. The rover descended slowly, dangling from the sky crane, until its wheels touched the surface. The cables were cut. The sky crane flew away and crashed a safe distance from the rover. The entire sequence, from atmospheric entry to wheels on the ground, took 7 minutes. During those 7 minutes, the signal from Mars took 14 minutes to reach Earth. This meant that by the time Mission Control received confirmation that the spacecraft had entered the atmosphere, it had already been on the surface for 7 minutes, either intact or in pieces. There was nothing anyone on Earth could do. The entire landing was automated. The spacecraft had to do everything on its own. It worked perfectly. The room at the Jet Propulsion Laboratory erupted. Engineers who had spent years designing and testing and agonizing over every component hugged each other, wept, and cheered. The signal that confirmed touchdown, a simple data packet that had traveled 248 million kilometers at the speed of light, represented one of the greatest engineering achievements in human history. What makes the sky crane even more remarkable is the precision involved. Curiosity did not just land on Mars. It landed on a specific spot on Mars. The landing target in Jezero Crater was a 12 by 7 kilometer ellipse at the base of Mount Sharp, and Curiosity touched down within 2.4 kilometers of the center of that ellipse. After traveling 567 million kilometers through interplanetary space over 8.5 months, the landing was accurate to within a fraction of a percent on Earth. That is like throwing a basketball from London and hitting a specific spot on a basketball court in New York City. The sky crane landing is, in many ways, a metaphor for Mars exploration itself. It is audacious, improbable, requires years of preparation and extraordinary precision, and when it works, it produces results that transform our understanding of the universe. Perseverance used the same sky crane system in 2021, and it worked perfectly again. Now, let us leave the surface for a moment and look at Mars from above, from orbit. Because some of the most important discoveries about Mars have come not from rovers on the ground, but from spacecraft circling overhead, mapping the planet in extraordinary detail. We have already talked about the ancient ocean evidence and the underground water debate, but there is another discovery from orbit that deserves attention, one that speaks to the sheer scale and violence of the geological forces that shape Mars. This is shocking discovery number 6. Mars is home to the most extreme geological features in the solar system, Olympus Mons. You have probably heard of it. It is the largest volcano and the tallest mountain in the solar system. 21.9 kilometers high, 2.5 times the height of Mount Everest. But height alone does not capture the scale of Olympus Mons. The volcano is 600 kilometers across at its base. If you placed it in the United States, it would cover the entire state of Arizona. Its caldera, the collapsed crater at its summit, is 80 kilometers wide and nearly 3 kilometers deep. You could fit the entire island of Manhattan inside the caldera with room to spare. But here is the detail that really puts Olympus Mons in perspective. The slope of its flanks is so gentle, only about 5 degrees, that if you were standing on its lower slopes, you would not know you were on a mountain. The curvature of Mars would hide the summit below the horizon. You would think you were standing on a flat plain, not on the side of the largest volcanic structure in the known universe. How does a volcano get this big? The answer reveals something fundamental about the difference between Mars and Earth. On Earth, volcanic hotspots exist where plumes of hot material rise from deep in the mantle. Hawaii is the classic example. A stationary hotspot feeds magma to the surface, building a volcanic island. But Earth's tectonic plates are moving, so the plate carrying the island slowly drifts away from the hotspot. The volcano goes dormant, and a new volcano forms over the hotspot. This is why Hawaii is a chain of islands, each one formed over the same hotspot and then carried away by plate motion. Mars does not have plate tectonics. Its crust is a single, unmoving shell. So when a hotspot feeds magma to the surface, the volcano just keeps growing, and growing, and growing. For billions of years, the same volcanic vent has been pumping lava onto the same spot, building Olympus Mons into the colossal structure we see today. The most recent lava flows on Olympus Mons are estimated to be only about 200 million years old, young by geological standards. The volcano may not be entirely extinct. And then there is Valles Marineris. If Olympus Mons is the largest mountain in the solar system, Valles Marineris is the largest canyon. It stretches for over 4,000 kilometers across the Martian equator, roughly the distance from New York to Los Angeles. At its widest, it is 200 kilometers across. At its deepest, it plunges 7 kilometers below the surrounding surface, more than 4 times deeper than the Grand Canyon. But Valles Marineris is not a canyon in the way the Grand Canyon is a canyon. The Grand Canyon was carved by the Colorado River over millions of years. Valles Marineris was not carved by anything. It is a tectonic rift, a crack in the Martian crust caused by the swelling of the Tharsis volcanic region to its west. As the Tharsis bulge grew, inflated by billions of years of volcanic activity, it stretched the crust until it fractured. Valles Marineris is the scar. The formation of Valles Marineris was not a single event. It developed over billions of years, and evidence suggests that water played a role in shaping it. Some sections of the canyon show layered sedimentary deposits that may have been laid down by ancient lakes that filled portions of the rift. Others show signs of landslides so massive that they make the largest landslides on Earth look trivial. Walls of rock that collapsed and flowed across the canyon floor, traveling hundreds of kilometers before coming to rest. In 2023, the Mars Express orbiter discovered deposits of hydrated sulfate minerals, salts that form in the presence of water, deep within Valles Marineris. The discovery suggests that liquid water persisted in the depths of the canyon long after it had vanished from the surface elsewhere on the planet. The canyon's depth may have created a microenvironment where atmospheric pressure was high enough and temperatures warm enough for liquid water to survive for millions of years after the rest of Mars had dried out. If life existed on Mars and was driven underground by the deteriorating surface conditions, places like the depths of Valles Marineris would have been among the last refuges. Imagine standing on the rim of Valles Marineris, looking across. The opposite wall would be so far away that it would be below the horizon. The canyon is wider than the curvature of Mars allows you to see across. You would not see a valley. You would see what appears to be the edge of the world, with nothing but haze and void beyond. This features Olympus Mons, Valles Marineris, the massive flood channels, the dichotomy between the northern lowlands and the southern highlands, paint a picture of a planet that was, for much of its history, geologically violent. Mars was not always the quiet, dead world it appears today. It was a world of eruptions and floods and tectonic upheaval, a world where geological forces operated on scales that dwarf anything on Earth. And the question that geologists are still working to answer is, when did Mars's geological engine finally wind down? Is Mars truly dead, or is it merely sleeping? Recent evidence suggests the latter. In 2022, analysis of seismic data from NASA's InSight lander, which operated on Mars from 2018 to 2022, revealed that Mars still experiences Marsquakes. Not just small tremors, but significant seismic events, including one with a magnitude of 4.7, the largest quake ever recorded on another planet. The seismic data also revealed that Mars's core is larger and less dense than expected, suggesting it contains lighter elements mixed with the iron and raising new questions about the state of the interior. The Marsquake data also told us something unexpected about the structure of Mars. InSight's seismometer detected two types of seismic waves, P waves and S waves, that travel at different speeds through different materials. By measuring the arrival times and amplitudes of these waves from Marsquakes on the opposite side of the planet, scientists were able to build the first detailed picture of Mars's internal structure. What they found was surprising. Mars's crust is thicker than expected, averaging about 40 to 60 kilometers, with the southern highlands being significantly thicker than the northern lowlands. This crustal dichotomy, the dramatic difference in elevation and crustal thickness between the two hemispheres, remains one of the great unsolved puzzles of Martian geology. Was it caused by a single giant impact early in Mars's history that excavated the northern basin? Or was it the result of internal convection patterns that thinned the crust on one side? The debate continues, but the InSight data has given scientists far better constraints on the problem than they have ever had before. InSight also detected seismic waves that had traveled through the Martian interior in ways that suggest pockets of partially molten rock may still exist beneath the surface. Mars may still have magma, not enough to drive plate tectonics or restart the magnetic dynamo, but enough to tell us that the planet is not entirely geologically dead. This matters for the search for life because geological activity means energy. Energy means heat. Heat means the possibility of liquid water at depth. And liquid water means the possibility of habitable environments that could persist even on a planet whose surface has been uninhabitable for billions of years. Let us now move to a topic that bridges the gap between Mars science and the broader question of life in the universe. Because the search for life on Mars is not just about Mars. It is about understanding a process that we currently have only one example of. This is shocking discovery number 7. And it is not about something we found, it is about something we realized. Here is the problem. We have exactly one example of life in the universe, life on Earth. Every living thing we have ever studied, from bacteria to blue whales, from archaea in volcanic vents to fungi in Antarctic ice, shares the same fundamental biochemistry. The same DNA, the same amino acids, the same basic cellular machinery. All life on Earth is, when you trace it back far enough, one family. This means we cannot answer the most fundamental question about life. Is it common or is it rare? Is the emergence of life an inevitable consequence of chemistry and energy, or is it a 1 in a trillion accident that happened to occur on our planet? Mars gives us the chance to find out. If we find evidence of past or present life on Mars, one of the first questions scientists will ask is it related to life on Earth? This is not a strange question. We know that rocks are regularly transferred between Earth and Mars by asteroid impacts. When a large asteroid strikes Mars, The impact can launch chunks of Martian rock into space with enough velocity to escape Mars's gravity. Some of those rocks eventually fall to Earth. We have found over 300 Martian meteorites on our planet. The process works in reverse too. Earth rocks have been launched to Mars by impacts here. If microbial life can survive inside rocks during the journey between planets, and experiments have shown that some extremophile organisms can survive the conditions of impact ejection, years of transit through space, and atmospheric entry, then life could have been transferred between Earth and Mars early in the solar system's history. This idea is called panspermia, or more specifically, lithopanspermia, life spreading between worlds inside rocks. If Martian life turns out to be related to Earth life, sharing the same DNA, the same amino acids, the same genetic code, it would mean that life originated on one planet and was transferred to the other. We might be Martian, or Martians might be Earthlings. Either way, it would mean that we still have only one example of life arising from non-life. But if Martian life turns out to be fundamentally different, using different amino acids, a different genetic code, a different biochemistry, it would mean that life arose independently on two separate planets, and that would change everything. It would mean that life is not a miracle. It is a process. Given the right conditions, liquid water, energy, the right chemistry, life emerges. It is what the universe does. The implications for the prevalence of life in the cosmos would be profound. If life arose independently on two planets in the same solar system, then the universe must be teeming with it. Every star with a habitable zone, every moon with a subsurface ocean, every world with liquid water and energy, all of them become candidates. This is what is at stake in the search for life on Mars. It is not just about finding microbes in ancient rocks. It is about answering the deepest question we have ever asked. Are we alone in the universe? And this brings us to a broader reflection on what Mars teaches us about planets and life and the fragility of habitable worlds. Consider the numbers for a moment. Earth and Mars orbit the same star. They sit in the same general neighborhood. Mars averages about 1.5 times farther from the Sun than Earth. In cosmic terms, this is nothing. The nearest star to our Sun is over 4 light-years away, almost 300,000 times the Earth-Mars distance. On the scale of the galaxy, Earth and Mars are essentially in the same spot. Mars and Earth formed from the same cloud of material, at roughly the same time, in roughly the same region of the solar system. They started with similar ingredients. For hundreds of millions of years, both planets had liquid water, thick atmospheres, and the chemical building blocks of life. But their fates diverged. Earth, larger and more geologically active, maintained its magnetic field, kept its atmosphere, and sustained the conditions for life for 4 billion years and counting. Mars, smaller and less geologically active, lost its magnetic field, lost its atmosphere, and became the cold desert we see today. The difference was not destiny. It was mass. A few more impacts during Mars's formation, a slightly thicker mantle, a slightly larger core, and Mars might have held onto its magnetic field. It might still have oceans. It might have developed complex life. We might be looking up at a blue star in our night sky instead of a red one, wondering if there were people looking back at us. This is a humbling thought. Our own planet's habitability is not guaranteed by any cosmic law. It is the product of a specific combination of size, composition, distance from the Sun, and geological activity. A combination that could easily have been different. Earth is not inherently special. It is fortunate. And Mars is a warning, a reminder that habitable conditions are not permanent, that worlds can die, that the difference between a planet that sustains life for billions of years and a planet that loses everything can come down to factors as mundane as how much iron is in the core. There is another dimension to the life on Mars question that we should touch on, because it connects Mars to a much wider cosmic perspective. In recent years, astronomers have discovered thousands of exoplanets, planets orbiting other stars. Many of them orbit within their star's habitable zone, the region where temperatures allow liquid water to exist on the surface. Some of these planets are rocky, roughly Earth-sized, and receive roughly the same amount of energy from their star as Earth receives from the Sun. But here is the thing we often overlook. Many of these potentially habitable exoplanets orbit red dwarf stars, small, dim stars that make up about 70% of all stars in the galaxy. Red dwarfs are so dim that their habitable zones are very close to the star. Planets in those zones are likely tidally locked, one side always facing the star, the other always in darkness. They are bombarded by powerful stellar flares. They may lack magnetic fields strong enough to protect their atmospheres. In other words, many of the potentially habitable exoplanets we have discovered may face the same challenges that killed Mars: magnetic field loss, atmospheric stripping, surface sterilization. The Mars story is not just a local tale. It is a template for understanding what may happen to billions of worlds across the galaxy. By studying how Mars lost its habitability, we learn what to look for and what to worry about when we assess the habitability of exoplanets light years away. If life can survive on Mars despite all of these challenges, hidden underground, clinging to subsurface water, feeding on chemical energy, then it can survive in similar environments on countless other worlds. Mars becomes not just one planet's story, but a universal case study in the resilience of life. Now, let us turn to the future, because the story of Mars exploration is far from over. In fact, some scientists believe we are entering the most exciting era in the history of Mars science. Over the next decade, several missions are planned that will push our understanding of Mars further than ever before. ESA's Rosalind Franklin rover, named after the chemist whose work was crucial to the discovery of DNA structure, is designed to drill up to 2 meters beneath the Martian surface. This is important because the surface of Mars is bathed in harsh ultraviolet radiation and bombarded by cosmic rays, conditions that would destroy organic molecules and kill most known organisms. But beneath the surface, shielded by rock and soil, conditions are far more benign. If life exists on Mars today, or if well-preserved organic material from the ancient past survives anywhere, it is most likely underground. The Rosalind Franklin rover carries an instrument called the Mars Organic Molecule Analyzer, MOMA, which can detect organic molecules at concentrations far below anything previous missions could measure. If there are organic signatures hiding beneath the surface, MOMA has the best chance of finding them. The Rosalind Franklin rover also carries a camera system and spectrometers that can analyze the mineral composition of exposed rock layers, giving scientists a window into the subsurface environment without needing to drill. Its landing site, Oxia Planum, was chosen because orbital data shows an abundance of clay minerals, the same type of minerals that form in the presence of water with a neutral pH. Clay minerals are excellent at preserving organic molecules because they form layered structures that can trap and protect delicate organic compounds from radiation and oxidation. If ancient organic material survives anywhere on Mars accessible to a surface mission, Oxia Planum is one of the most promising places to look. And beyond the rovers, there are concepts on the drawing board that go even further. Proposals for a Mars ice mapper, an orbiter with advanced radar that could create a detailed three-dimensional map of subsurface water ice across the planet. Proposals for a Mars Life Explorer, a lander that would carry a suite of next-generation life detection instruments far more capable than anything previously sent. Proposals for a helicopter-based mission that would explore the walls of Valles Marineris or the slopes of Olympus Mons, visiting terrain too rough and too remote for any rover. And then there are the sample return concepts. Despite the budget and schedule challenges facing the current Mars sample return architecture, the scientific community remains committed to bringing those Perseverance samples home. Alternative concepts are being developed that could reduce the cost and complexity, including proposals that would use commercial launch vehicles and simpler mission designs. The consensus among scientists is clear. Getting those Jezero rocks to Earth laboratories is the single most important near-term objective in planetary science. There is one more mission concept that deserves mention because it represents a philosophical shift in how we approach Mars exploration. For decades, our Mars missions have been designed primarily to study geology and look for signs of past life. But a new generation of mission concepts is focused on something different, searching for present life. The most ambitious of these is the Mars Life Explorer concept, which would carry instruments capable of detecting active metabolism, not just the chemical fossils of life that existed billions of years ago, but the metabolic signatures of organisms that are alive today. The mission would target regions where subsurface water is most likely to exist, drill into the permafrost, and analyze the extracted material for signs of active biological chemistry, energy consumption, waste production, molecular replication. If such a mission were to find active life on Mars, it would not just be a scientific discovery. It would be a civilizational event. It would force us to rethink our plans for Mars, colonization, terraforming, resource extraction, because we would no longer be dealing with a dead world to be reshaped at will, but a living world that raises profound ethical questions about our right to alter it. This is a conversation we need to start having now before we find ourselves making irreversible decisions. Because if Mars is alive, we have responsibilities to it. And if it is dead, the way it died has lessons we cannot afford to ignore. Now, let us take one more detour before we approach our conclusion. Because there is one more aspect of the Mars story that we have not yet explored. And it is perhaps the most mind-bending of all. Let us talk about Mars in the context of time. We have been discussing Mars as it is now and as it was 4 billion years ago. But what about the far future? What happens to Mars and to our relationship with Mars over the coming billions of years? The Sun, like all stars, is gradually getting brighter. Over the next billion years, the Sun's luminosity will increase by about 10%. On Earth, this will have devastating consequences. Rising temperatures will eventually cause the oceans to evaporate, turning Earth into a Venus-like hellscape. Models suggest Earth may become uninhabitable for complex life within about 1 billion years. But for Mars, the increasing solar luminosity is actually good news. As the Sun gets brighter, Mars gets warmer. Over the next several billion years, temperatures on Mars will gradually rise. The polar ice caps will begin to sublime. Carbon dioxide trapped in the soil may be released back into the atmosphere. Mars will develop a thicker atmosphere and higher surface temperatures. In about 3 to 4 billion years, Mars may become more habitable than it is today, just as Earth is becoming less habitable. The habitable zone of our solar system is very slowly moving outward. Mars will eventually be in a sweeter spot than it is now. It is a strange irony. The planet that is dying today may become more habitable as our own world becomes less so. If humanity survives long enough, if our descendants are still here in a billion years, they may look at Mars not as a frontier to be conquered, but as a refuge. A world that was once too cold, slowly warming to just the right temperature as the sun's increasing luminosity pushes the habitable zone outward. The planetary cycle of habitability, turning on timescales so vast that our entire recorded history is less than a pixel in the image. Of course, by that time, the Sun will be approaching the end of its main sequence life. About 5 billion years from now, the Sun will begin to swell into a red giant, eventually expanding to a size that will engulf Mercury and Venus and possibly Earth. Mars will survive the red giant phase. It is far enough from the Sun, but it will be scorched by the intense heat and radiation of the expanded star. And after the red giant phase, the Sun will shed its outer layers and collapse into a white dwarf, a dense, slowly cooling, stellar remnant no larger than Earth. Mars will continue to orbit this white dwarf, a frozen relic circling a dying star, carrying in its rocks the entire history of the solar system, including, perhaps, the record of life that once existed on its surface. And in the very far future, trillions of years from now, long after even the white dwarf has cooled to a black dwarf, long after all the stars in the universe have burned out, Mars will still exist. A frozen, dark world drifting through a universe of absolute blackness, carrying in its ancient rocks a record of everything that once was. The rivers that flowed, the oceans that filled, the magnetic field that shielded, the atmosphere that vanished, and perhaps, the microbes that lived and died in the warm mud of a young planet 4.5 billion years ago, in a corner of the cosmos where something remarkable happened for a little while. It is a strange and melancholy thought. Mars, the planet we are exploring today, with robots and orbiters and drones, will outlast the Sun. Long after every human civilization has risen and fallen, long after Earth itself has been consumed by the swelling Sun, Mars will still be there, a silent, frozen monument to a solar system that once harbored life. But let us not end on melancholy. Let us end on wonder. Because the Mars story, at its heart, is a story about curiosity. The same curiosity that drove the first humans to look up at the night sky and wonder what those wandering red lights were. Mars has been a companion to humanity for as long as we have existed. Mars has been called the abode of the gods, the harbinger of war, the home of canals built by a dying civilization, the next frontier for human expansion. Each generation has projected its own hopes and fears onto that reddish dot, and each generation has been wrong, but beautifully, productively wrong in the way that drives us to look harder and learn more. The Egyptians called it Hardesher, the red one. The Babylonians named it Nergal, after their god of war and plague. The Greeks called it Ares. The Romans called it Mars. Every civilization that ever looked up at the night sky noticed this bright, reddish point of light that moved against the background of fixed stars, and every civilization gave it a name and a story. And now, after thousands of years of wandering, we are there. Not in person, not yet, but through the eyes and hands of machines we built and sent across hundreds of millions of kilometers of empty space. Machines that have driven across ancient lake beds, drilled into rocks that formed before any life existed on Earth, and tasted the Martian wind. We have found a world that was once warm and wet and possibly alive. A world that was killed by the loss of its magnetic field and the slow erosion of its atmosphere. A world that may still harbor liquid water beneath its frozen surface. A world where the most important rocks in the history of science sit waiting inside sealed tubes, promising answers to questions that have haunted humanity for millennia. Are we alone? We do not know. Not yet. But we are closer to answering that question than we have ever been. And the answer, when it comes, will come from Mars. Think about what that means. Somewhere in the universe tonight, in a crater on a cold, rust-colored planet, beneath a sky the color of butterscotch, a small robot is sitting in the dark. Its cameras are powered down. Its instruments are sleeping. But inside its belly, sealed in titanium tubes, it carries rocks that might contain the fossilized remains of organisms that lived and died billions of years ago on a world that no longer remembers them. Those rocks are waiting for us to come and get them, waiting for us to bring them home and crack them open in the sterile white rooms of our laboratories, waiting to tell us a secret that has been locked in Martian stone for longer than complex life has existed on Earth. And whatever those rocks reveal, whether they contain the unambiguous signatures of ancient life or the frustrating absence of it, the act of reaching across the void to retrieve them is itself a kind of answer. It tells us something about what life does when it becomes aware of itself. It reaches out. It asks its questions. It refuses to accept that the darkness beyond the campfire is empty. Mars is not just a planet we are exploring. It is a mirror, a reflection of what Earth was, what Earth could have been, and what Earth might become. In its dry riverbeds and ancient lake shores, we see the ghost of a world that was, for a time, remarkably like our own. In its thin atmosphere and frozen surface, we see what happens when a planet loses the geological engine that sustains habitability. And in the possibility that life once existed there, or exists there still, clinging to some dark, wet pocket beneath the ice, we see the resilience of the most remarkable phenomenon in the known universe. Life is fragile. Worlds can die. Atmospheres can be stripped away. Oceans can vanish. But life, when it takes hold, has a way of finding places to hide, niches to fill, conditions to exploit. If life arose on Mars and survived the loss of its oceans, the collapse of its atmosphere, the bombardment of its surface by radiation, if some microbial colony found a way to persist in the salty darkness beneath the ice cap, feeding on chemical energy, generation after generation, for 4 billion years, then that would be the most extraordinary survival story in the history of the universe. And it would mean that the universe is not empty. It would mean that wherever water flows and energy exists and chemistry unfolds, life is waiting to emerge. On icy moons around distant gas giants, in the subsurface oceans of Enceladus and Europa, on rocky planets circling red dwarf stars in systems we have not yet discovered. Life finding a way, always. Tonight, Mars is in the sky. Depending on when you hear this, it may be a bright amber dot above the horizon, or it may be hidden below the rim of the world, waiting to rise. But it is there. It is always there. Our nearest neighbor, our sister world. The planet that came so close to being another Earth and lost everything except its secrets. We have sent our machines to pry those secrets loose, and slowly, patiently, one rock at a time, one analysis at a time, one discovery at a time, the planet is answering. We just have to listen. So let tonight be quiet. Let the weight of the day fall away. Let your mind drift across the 200 million kilometers of empty space between here and there to a world of rusty plains and ancient craters and a sky the color of a faded sunset. A world where rovers sit in silence, where the wind whispers across dunes of iron oxide, where the ghosts of ancient rivers are carved into stone that has been waiting, patient and cold, for someone to come along and read them. The story of Mars is not over. It is barely beginning. And whatever comes next, whatever those rocks reveal, whatever future missions discover, whatever truths are hiding in the frozen darkness beneath the Martian poles, one thing is certain. We will keep looking. We will keep asking. We will keep sending our instruments and our curiosity across the void. Because that is what we do. That is what life does. It reaches for the unknown and tries to make it known. And that, when you think about it carefully, might be the most important thing we have ever learned about Mars. Not that it once had oceans. Not that it might have harbored life. Not that its magnetic field died or its atmosphere bled away into space. The most important thing is simply this: we cared enough to find out. Good night. Sleep well. Rest easy. And when you close your eyes, know that somewhere out there, on a cold and quiet planet, a little machine is keeping its patient, quiet watch for all of us, waiting for the day when we finally come to bring it home.